Hello everyone and welcome to this lecture. Today we're going to explore one of the most widely used and intuitive algorithms in all of machine learning and data analysis, k-means clustering. By the end of this lecture, you'll understand exactly what clustering is, why we do it, how k-means works step by step, and how to apply it to real data. We'll also walk through worked examples so that the math becomes crystal clear. Whether you're brand new to this topic or just trying to improve your understanding, stick with me. This is one of those algorithms that once it clicks, you'll start seeing application for it everywhere. So let's get started. So before we dive into the mechanics, let me frame this lecture around 4 questions that you can see here, and we'll answer them one by one. So first, what is clustering? Next, we'll ask why would we want to cluster data? Next, how do you determine clusters? And finally, how can you do this efficiently? Think of these as signposts. Every major section of today's lectures answer one of these questions, so keep them in mind as we go. So first, what is clustering? What is exactly, what exactly is clustering? So the formal definition says clustering is the classification of objects into different groups, or more precisely, the partitioning of a data set into subsets called clusters, so that the data in each subset share some common trait, often according to some defined distance measure. So let me make that concrete with a simple analogy. Imagine you walk into a large library and all the textbooks are just piled randomly on the floor. Clustering is the process of grouping these books in a way that makes sense, maybe by genre, maybe by reading level, or by topic. After clustering, each shelf holds books that are similar to each other. You haven't been told in advance exactly how to group them. You're discovering the groupings that make sense from the data itself. So this last part is very important. Clustering is an unsupervised learning technique. There are no pre-labeled categories given to us. The algorithm figures out the structure of the data on its own. Another real-world example, let's say a supermarket, might cluster its customers based on their purchase history, without being told which customers are deal hunters or brand loyalists, and discover those segments naturally. So this is the power of clustering. Now let's look at the different types of clustering. There are 2 main families essentially: hierarchical algorithms and partitional clustering. So now that we know what clustering is, let's look at the landscape of clustering algorithms so you understand where k-means fits in. There are 2 broad families. The first is hierarchical algorithms, and these build clusters by either combining smaller clusters into larger ones or breaking larger clusters into smaller ones. The bottom-up approach starts with every single data point as its own cluster, and then repeatedly merge the 2 closest clusters until you end up with one big cluster. You can stop the merging process at any point to get a desired number of groups. The top-down approach does the opposite. You start with everything in one big cluster and keep splitting it. Think of it like a family tree being split into branches. The second family is partitional clustering. These algorithms determine all clusters at once in a single pass. K-means is the most famous example of this family. Others include fuzzy C-means, which allows data points to belong to multiple clusters with varying degrees of membership, and QT clustering algorithm, which tries to find high-quality clusters based on a quality threshold. So for the rest of this lecture, we're going to be focusing on k-means, which is part of a partitional category. Now, before we can cluster anything, we need a way to measure how similar or how different two data points are. That's where distance measures come in. The choice of distance measure influences the shape and quality of the clusters you discover. The slide here shows common measures, 6 common measures. Let me walk through each of them. Number 1 is called Euclidean distance, also called the two-norm distance. This is one of the most popular measures. It's a straight line distance between 2 points, essentially. If you have 2 points in 2D space, say coordinates 1 and 2, 4 and 6, you just apply Pythagorean theorem, and this gives you the distance between them. In higher dimensions, it generalizes naturally by summing the square differences across all dimensions and taking the square root. This is the distance measure used in most standard k-means implementations. The second measure is called Manhattan distance, or also called the taxi cab norm or one norm. Instead of going in a straight diagonal line, you travel along the grid, like navigating city blocks. So you can only move horizontally or vertically. This measure is less sensitive to outliers than Euclidean distance. The next measure is called maximum norm, and here you take the largest possible difference across any single dimension. So this one is useful when you care most about the worst case differences in any one feature. The next distance measure, Mahalanobis distance, this is more sophisticated. It accounts for the correlations between variables and the scale of each feature. If your data has features measured in different units, like heights in centimeters and income in thousands of dollars, this measure corrects for those differences. Number 5 is the inner product space or cosine similarity. So instead of measuring straight line distance, you measure the angle between two vectors. This is extremely popular in text analysis. Two documents that use the same words in similar proportion will have a small angle between them, even if one document is much longer than the other. And finally, number 6, Hamming distance. This measures how many positions are different between two strings. For example, the words cat and bat have a Hamming distance of 1 because there's only one character difference between both of them. This measure is used in genetics or in error correcting codes and natural language processing as well. For today's examples, we'll be using Euclidean distance, which is by far the most common choice for k-means. So, as we just covered, distance measures through 3 through 6 extend our toolkit from maximum norm to cosine similarity and Hamming distance. Keep in mind that the distance measure you choose is a design decision that shapes your entire clustering result. Different measures can produce very different clusters on the same dataset.